finish it up. So the last problem that I did, I remember doing this in class. This was the last problem that I did. What was this story? This story was that, let me draw quickly. So if this is x, this is y, this is z, that is a cylinder. The cylinder is actually x equal to y squared, a parabolic cylinder, right? In the xy plane, it looks like this. X equal to y squared looks like this. Hold on. X equal to y squared looks like that, right? So basically, it opens up this way. And I know basically it's going to be in the first quadrant, so I don't even put this part of it, just that part. Then I know that there is x equal to z, which is a plane that goes this way, right? A plane that is orthogonal to the line x equal to z in that plane, basically. And so what I know from there, I can sort of draw a picture. I know. I do this a lot in my office. This is going to be a parabolic cylinder, like that cylinder. If I cut it with this plane, what does it look like? Forgot my scissors. But it's a cut like that, right? You have a pipe, you cut it. But not orthogonally, but on the, yeah. That looks like that. So that's what you're trying to get out of it. So it looks like sort of, wait. Oh, it's a full one. It is a full one. So it looks like that, basically. And that's the plane, x equal to z. That is the cylinder, x equal to y squared, and that's again the plane, x equal to 1. And that's the general shape of it. We set this up in z direction first, because z direction first was actually, what was it? It was simple z direction. When I'm looking at this, x direction is not simple. Can you guys tell x direction is not simple? Is it the lower surface problem or lower surfaces problem or upper? The upper, right? If I draw an arrow from here to here, if I draw an arrow in the direction x, then the lower surface could be the blue or could be the red. And the upper surface is always the green. In the y direction, I'm looking at the y direction. Put the y to your nose. Put the y to your nose to see what's going on. I see the projection on xz plane. Right now, I'm watching the projection on xz plane. And on xz plane, basically, what I see is this triangle, and I can tell that the surfaces in the y direction, lower and upper, were both the cylinder. Cylinder was the upper and lower surface. Now, what we set up was in the z direction. I'm putting it in the z direction. I have to turn it around a little bit. In the z direction, it looks like that. If I put it toward my nose, and this surface is purple, the lower surface is purple again. It's the z equal to 0. That's the one that we set up, z direction first. What I say, how many of you guys had CAD in high school? A few. What I see is a lot of gentlemen had CAD, a lot of ladies haven't had CAD. And that, unfortunately, creates some disparity as it is, because CAD seems like something that we don't do. But it's very useful in imagining 3D. What I want to say is that you can look at the GeoGebra if you haven't had CAD. And it basically brings up your chances as understanding in 3D. Looking at the GeoGebra sheet helps. My complaint was literally this, because my daughter was the only one in CAD class in her high school. Encourage everybody else to actually, that are interested in higher math to take that CAD course. So now that I discussed this, what are you guys expecting me to do for next? The next thing that I want to say is this. How about I find, what direction was it non-simple? What direction was it non-simple? In the X direction, right? Y direction was okay. This is Y direction. You can see that the surface, there's only one color, right? But when I'm looking at the X direction, I see two colors. So I want to go with the X direction. X direction first. X direction, when I draw an arrow, I could go from this surface to X equal to 1. There is the region when X starts from the plane, Z, and then ends at 1. And then there is another region, X starts at the cylinder, which is what? X equal to Y squared, and ends at 1. Two regions. Everybody agrees on that. Can you guys see it in here? Again, practice a lot with GeoGebra if you haven't had CAD. So one is this, one is that. Now I'm trying to say, what are the projection of each region? Let's call this region 1, region 2. Now I'm looking at the projection. Remember for me, purple is the plane, blue is the other, what is that called? Cylinder. Now, if I'm projecting, can you see that the purple looks like above a parabola? The blue looks like below that parabola. So I have two. Which one is this? Purple? Purple is above the parabola, correct? Purple is the plane above the parabola. So if I'm projecting on YZ, what I see is this is going to be above the parabola. And this one has to be below the parabola. Parabola. One more try, one more try. If I call it parabola, it's going to be parabola. So two of these. Fair game? Now, what remains, I'm saying XZ, right? No, YZ. Projection on YZ. X is used. X is going to be the most inner. Correct? X is the most inner, so X is used. So I'm on YZ plane. When I'm looking at the YZ plane, let's go back to the variables. Right, oh, sorry, the original variables. Where are the original variables? I had the solution up. There we go. The original variable, that's the parabola that I have. But that's not in YZ. So what should I do? Let me tell you, where does this parabola come from? It's basically the shade of this thing, the shadow of that thing. It's the shadow of where the purple meets blue. The next time, I'm not explaining it in so many details. The first time around, I want to explain it in a lot of details. Where these two meet is the shadow of that on the YZ plane is going to be that parabola. So how do I find it? It's the basic of it is that you parameterize and you find the shadow. But that parameterization and finding the shadow can be summarized in this process. Can you guys remember the process? We're parameterizing and then finding the shadow, but you really don't have to go through all the process. All you need to do is take that and intersect it. See, it's the intersection of these two that is parameterized. So you just intersect those two, x equal to y squared and x equal to z. You eliminate the variable that you don't want. Which variable do I not want after the most inner? X. Most inner is x. I already set it up. Surface to surface, right? This is surface to surface, I set it up. Most inner surface to surface, and I set it up. So I eliminate x between the two of them. What do I get? Z equal to y squared. So this is going to be z equal to y squared, and that is going to be z equal to y squared. And can you guys tell me what is the upper bound here? Where does the biggest z happen here? Let's bring back the picture. It would be 1, right? At very top, they meet at 1. So the top part is just z equal to 1. In here, can you guys tell me what is the smallest and highest y value? You can look at the picture. -1 and 1. Everybody agrees on that? Everybody can see that much. And then please practice a few, quite a few for this part. Try to even graph the picture on your own, and there are some assignments that you do that. You graph the picture on your own so you know what's going on in 3D. I will give you the picture on the exam, but I want you on some assignment to try it. Why? Because it improves your imagining 3D objects. That's all it is to it, basically. So now, I set this up. The most inner is that one. How do I set up the two outer one? The most inner is the dx. X goes from 1 to z. The most inner for this region is dx. It runs from y squared to 1. Oh, did I switch? How did I? No, I didn't switch. I'm good. I am good. Except I switched this too. I did switch. Z to 1. Z to 1. Y squared to 1. The most inner. Now let's set up the double outside. How do I set up the double? Over here. Should I do vertical or horizontal? Vertical? Vertical is in what direction? Z. So I have the Z here. Z start at what? No, Z starts at this. Look, the arrow is right here. Y squared to 1. Then, oh, I forgot to find these bounds. I found it over here. You guys found it for me. dy from -1 to 1. And over here, should I do the same thing? I could do that, right? Vertical. So dz first, but then it goes from 0 to y squared, and dy goes from -1 to 1. And then you add the two together. Was there a function or was it just one? It was just one. Did that make sense a little bit? Yes.
Yeah. So on the part that says reach y squared plus the actual equal 1, why would we shade in below the curve?
This one? That one. The other one. Hold on. Let's look at this picture one more time. when, before rotation, blue is the cylinder, and then the purple is a plane. The red or purple. That's purple, I think. Red. So the red is the plane. Blue. And now let's look at this. The red is the plane. We start at the plane. Here's the plane. And we end at 1. Red is up there, right? And then the other one is it starts at the cylinder. We're shading these two are the projection on the. Exactly. You're shading the projection that has that over it. Basically, here below it, there is a plane. Above it is another plane, this region. That region below it is a cylinder. Above it is a plane. I'm integrating the shaded region. But for the plane to plane, this one, shaded region for plane. This is plane, right? It starts from plane to plane. And then another shaded region from cylinder to plane. Wait, the red here, that's a plane. That's a plane to plane. The other one is the cylinder to plane. Fair game? The first time around is a little bit wonky, but then it gets better. So our purpose in class is to find a simple region if it's possible. Sometimes it's not. You will get one that is not eventually in the lab. But if you have a simple region, we want you to compute the simple region. But the problem with that is that if you don't know how to deal with non-simple regions, you cannot recognize the simple regions well. So we have to discuss the non-simple regions. Focus is on simple regions, but we will give you some non-simple regions. Fair game? To understand it. Okay, so your turn, I think? No? No, yeah. It is your turn. There we go. This one is a quick one. The next one is more worky. There's the next one. Sorry. Didn't mean to put it there. I did. Do you guys have the shape? This is the shape. Which one? Think about the 3D picture. I want you to think about the 3D picture. But the next thing that I wanted you to do is to imagine what surfaces can cause problem. Which direction is not simple? Yes. I'll be back here. You put the nose to axis, and if you have multiple surfaces, either on the bottom or top, in that direction, yeah, it's not simple. I'm going to tell you one more trick at the moment. I just want you to think about the 3D first. What's that? You're good. You're good. Look, what's the question?
Do you mean simple as in like from plane to plane?
It's either from plane, the same plane to same plane all the times, or from same curvy surface to same curvy surface all the times, right? It just doesn't change. So the lower and upper don't change.
So then,
You good?
would it like? I feel like the XY plane and then that y plus z equal 2 plane would be the simple way to go about it, right?
So there are two simple ways to go about it.
Okay.
One way is going to up way, and then the other way is to go
So then, would you say z simple?
Z simple is true.
Okay.
One more is true.
Would you say x simple?
So what is not simple?
Y.
So I think it's time to tell you one more trick. Now that you have pondered upon it a little bit, it's time. It's time to tell you one more trick. So I'm looking at this and I'm confused. Where do you guys see a variable repeated out of these surfaces? Y is repeated, right? You also have y equal to 0, which is the lower. But the upper part has two surfaces associated with y. So if I get confused by the 3D picture, I look at the 3D picture that way. Here is an upper bound for y. Here's another upper bound for y. Therefore, it's not y simple, right? It's the same shape over there. Everybody agrees on that? Should I stop? 4. 1. Yeah. 4, 3, 2, 1, 0. What just happened? I thought I gave the... So now I want to discuss this. Sometimes they ask you to change the order for triple integral. And that's a valid thing to do also. So if I want to change the order, first of all, what do I do? For double integral, what did I do first when I was changing the order? I would find the inequalities and find the shape, right? Find the inequalities and find the shape. So how do I find the inequalities? Can you guys tell this is related to z? This integral related to z. Z is between what and what? 0, 2 minus y. Then I have x related to that one. So x is between 0 and 4 minus y squared. And then I have y is between 0 and 2. And then it's asking me to basically swap it between dx and change the order to dx first, then dy, then dz. That's what it's asking me. So looking at the picture, I see z is between 0 and 2 minus y, right? And then I see basically x is between 0 and 4 minus y squared. Hey, these are not even related. I could do this without the picture if I want to, because the bounds are both related to y, and y is outside. So I can swap this basically a little bit. That's one thing that I could have done. I know that x is going to be between, the most inner still between 0 and 4 minus y squared, which is right here. And so let's start with the picture also. Now I'm looking at this. X goes from 0 to 4 minus y squared, and that's fine. Now let's see what's the relationship between z and x. Z and y, sorry. What is missing? Z and y. So let's find that relationship. So that relationship between z and y, I can even look at this and tell there is a little line over here between z and y. Can you see this projection? It's right there. So z, y, and z. And then I have to figure out what this line is. But that line is already given to me. Where is that? Z equal to 2 minus y. Z equal to 2 minus y. And then I have to figure out y is between 0 and 2. Now let's swap the direction. I want y first. Right? I want y first, then z. So vertical. And vertical goes from, let's solve for y. What? You guys are welcome to stop me. It's y and z. Which direction? It's horizontal, right? In the y direction. So now solve for y. Y is equal to 2 minus z. So that is going to go in here. Let me see. I forgot to put in dx. dx goes from 0 to 4 minus y squared. Now y goes from 0 to 2 minus z. And z goes from what to what? 0 to 2. And that's the setup. So you can exclusively for this one, because both of the integral were, this region is both x simple and z simple. I could have done it by just the algebra of things or looking at the picture. Either one would work. But you have to kind of tell the picture from these inequalities, which the first one gives you z equal to 2 minus y squared, y, x equal to 4 minus y squared, and y equal to 2. And then from there, you basically pick up. Fair game? Questions? Are we good? You guys want to try? Let's try one. And so there is a non-simple one of these that you do in lab. The non-simple for this one you do in lab. I did one non-simple, you do one non-simple in lab. Right? Because you have to kind of learn it. Okay. This one you can both use the shape but write it down. Z is between what and what? 0 and y squared, z equal to y squared. Then what is y between? -1 and 1. What is x between? 0 and 1. Now, the order that they want is dx first. So what is x between what two shapes? Two surfaces. Look at the x. Look, what do you see in the back of x? Do you see a plane? You see a plane, right? The surface is a plane in the back. What about the front of z? If I do an arrow in z direction. It's just that piece of, under that parabola of the plane. It's a plane, but under that plane. So this is one of those questions that you can move things around. because not all the variables are connected, and everything is simple. You can move things around by just looking at the inequalities. Does everybody have the inequality that we have right now? Move it around. You can swap it. This is one of the occasions. Not very often you can do this. Does that make sense? Yeah, we're good? So you can move things around. Gosh, dang it, I took too long. I want to give you a little bit of time, but this is one of those things that you want to try a few times. Okay, so you can do it algebraically because you can swap them around. But look at this. What is this surface? If I'm looking at it, what is this surface? A plane that is cut. A plane that is cut in the x direction. This one is a plane that is cut in the x direction. Then you end up with this shape. How do I set up? This is y direction and that's a z direction. When you do the cut, sorry, this is from the last piece. When you find the x, then you end up with this shape. And it's asking you to go what direction? It says z first. Z first goes from that to that. Everybody followed? Are we good? No? What is this parabola? Z equal to y squared? Okay, so if I have most inner is what? Dx goes from what to what? It goes from plane z x equal to 0 to x equal to 1. Agreed? Yes. Now I have these two. And I want dz first and dy. Z goes from what to what? To y squared. What about y? Okay, which one is that? Okay. Huh? It's yeah. 4. Okay. Did everybody hear that? 4, 3, 2, 1, 0. I know how, but I'm not going to say it. It becomes true. The crowd stays the same because I think some people visit different classes also. So you don't feel like it's empty, but some of ours are not in here. Yeah. Can I do this one more time? Okay, we're starting the next section. I'm enjoying this so much. Next section is section 15.6. Do you guys remember the CU substitution from CAC 1? Yeah? Section 15.6. What was the story in CAC 1? U was equal to some g of x, right? And then what did you do? So you had a g of x, and you had this f of x dx. And when you did that, you would say du is equal to g prime of x dx. And then figure out how to incorporate this in here, right? This is the equivalent of that in 2 dimensions. It's called change of variables or transformations. So I start start with a motivating example. You guys want to be motivated, right? Correct? Yes. Have you had similar question to this in this section? On achieve, there's one question similar to that. How do I find the area of this thing? Okay, I can actually find the area of this thing. Can anybody tell me how? So I could do the integral, but integral I have to, how many simple regions is there? It's a lot. It's sort of messy to do this. I can do the geometry though. How do I do geometry, my friends? Exactly. I look at, did you see that I shaded this? That's 3/4 of the area pi 2 to the power 2. Agreed? Well, it's the radius is 2. No, the big one. The whole thing. The whole thing. If I go whole shaded here, can you see the shaded area? That's 3/4 of pi times 4. Then subtract the whole. That's again is 3/4 of a pi 1 to the power 2. So I have 3/4 of the, that's times 4, 3/4 of pi times 4 minus 1, which is 9/4 of pi. That's the area. Okay, how many of you ask yourself, why are we taking the integral of this thing over x and y? Why can't we do something else? Somebody please tell me, what else came to your mind when you saw that? Polar coordinates. Who said that? Thank you. Ian, thank you. So polar, no, wasn't you? Oh, it was Abraham. So polar coordinate comes in mind. Let me tell you, if I'm computing the polar coordinate, how would that be? You guys lead the way. What is d theta? 0 to pi over 2. What is r? What is the lowest r? 1 to 2. Let's integrate. I'm going to ask the next iClicker question is exactly what I'm saying right now. Honestly, just not even a little bit. You have to know it. So now what do I do? Integral inside would be theta between 1 and pi half dr. And then I get integral from 1 to 2 of pi half. Oh, it's 0. Minus 0 dr ends up to be what? Oh, 3 pi half. 3 pi half. Thank you. Very, very thank you. So, and then 3 pi half times 2 minus what? It's 3 pi half. Hey! What just happened? That these two are not equal. Why is it not equal? I need a scalar. So you actually cannot do that. If you're changing the variable to r and theta, this is the d region in x and y, dA of x and y. If you're changing that to the d region r and theta, dA of r and theta, you need something here. That something is the area scalar. Everybody so far with me? Honestly, I'm asking you that on the next iClicker. Oh, that's the entire story today. And on Friday. So basically, I want to say something. Do you see that 3 pi half? That 3 pi half is actually area of that. Do you see that? That's the area of that. I'm looking at the r and theta plane. And that integral that I wrote up there is the area of that. But I want area of this. So that scaling factor or something that I wrote in there is going to relate it, so we won't integrate over just find the area of that. We find the area of that scale to xy plane. I'm going to write these things out in a minute, but let's do an eye clicker because it's fresh in your mind. So which one is not right? 3 of them are correct, 1 of them is, should we switch? I think most of it is going to be covered on Friday. Guys, I know it's the day before the break, but come. This section is important. Which one gave me some problem?
Isn't that what we did last time?
Yeah, it's the one. It's right there. It didn't answer. Because we need something in the integral. Okay, Gabe? I'm just checking if you were paying attention. That's all I'm doing.
Do you multiply it by r to get the...
It turns out I multiplied by r. But I figured it out, and then you guys may have memorized some of those, which I say memorize them. But eventually what's going to happen is that we want you to be able to see any transformations and find it. Okay? Chloe, you go? You Chloe or not? You are Chloe. That's the same. Who's she? What is your name? Gwen. Sorry. I should know her name. I should know her name. She talked to me before. Good? That is the literal, that's a literal area. That's a literal area. That's a literal thing that didn't work. That's a literal thing that I used to compute it. And then that's a literal thing that it ended up to be. Huh? Oh, no. Yeah, maybe. No. 4, 3, 2, 1, 0. Was it too quick? Wait, what just happened? So we're talking about that. I actually wanted to say that before. Let's say it now. Please come on Friday. This section is very important, and I almost finish it on Friday. So what is happening here is that whenever I want to take the region that is in the xy plane, and take an integral of f of x and y, if I want to change the variable to another, let's say d of r and theta instead, and I will have then f of x of r and theta and y of r and theta, then I need, this Wednesday. I see why they're leaving. I posted a video, that last piece. Do it faster though. Everybody else is listening. What's that? Do it faster. No goodbyes. Just go. Oh, good luck, guys. Good luck. So you have to have something. This something is Jacobian of G. It's called Come on, a little faster, guys. It's kind of, I have to do the gavel. Okay, so that thing is going to be the Jacobian of G. So what is G? G of R and theta is going to be equal to X of R and theta and Y of R and theta. Can you guys tell me what X of R and theta is? Huh? Conversion formula. What is Y of R and theta? R sine theta. And that's the conversion formula. In here, the change of variable was, instead of X, I had R cosine theta instead of Y. In Calc 1, you only had one variable, right? U equal to G of X. In here, you have to say, well, I'm replacing X by R cosine theta, replacing Y with R sine theta. We use it, and it's kind of funky because yes, we find U again, but when we find U and V, then it would be G inverse, and I'll tell you why in just a minute. I have 2 more minutes. Can I talk over it a little bit more? You're good? You're good. So that's this story. That's a Jacobian of this. And Jacobian of that, let me write it down, is going to be the absolute value of abs for absolute value of the determinant of X sub R, Y sub R, X sub theta, Y sub theta. And it turns out every time it's similar. Eventually, I'm going to tell you that. Say again? And that would be I'm kind of getting ahead of myself a little bit. But I tell you how this thing works. One thing that is important, when I talk about transformations, again, I'm not going to go over the transformations today. Today, I'm just motivating you. Just motivating. So with transformations, you usually have variable U and V. Here were R and theta. In this situation was R and theta. Then your integral is in X and Y. This is the actual integral in X and Y over region D. But you get a region over here, then remember when you use substitution, you had to change the boundary. Do you remember that? The bounds. Here you change the region. So you find a region that is coming to that. So that would be a region over here. It may not be the same region. And we call this relationship G, as I told you over there. G, just G of U and V will give you X and Y. And if this is D, right, there was a region that gave me D. This region is going to be called G inverse of D. And do I have another minute? Should just like, that's the picture. And, oh, can I show you this quickly? People are laughing at that. Watch this and then go. Somebody tell me what happened. Transformation. Let me bring it back. Let me bring it back. Start over. Are these two rectangles the same in the grid in R and theta? These rectangles are transformed into those shapes. Are they the same area? No, that's the cool stuff. You answered that? Nick answered that. Okay, guys, I see you on Friday. I was going to cover a little bit more. Oh, yeah, adjournment.